This lab is on projectile motion. A projectile is an object projected or thrown that moves in a curved path acted on only by a single force, namely gravity. The shape of the path is actually parabolic, and the study of objects moving in these free flight paths is called ballistics. And you see examples of this all the time, particularly in sport. In the lab, you will fire projectiles at different angles, take key measurements, and look at how the quantities in these measurements are linked together by the equations of motion. Specifically, what you will do is vary the angle at which the projectile is fired and see how that affects how long the projectile stays in the air and critically how far it travels, its range or distance x. There are two scenarios. The first is a flat plane where the projectile is fired at the same height at which it lands on the flat surface, and the second one, it'll be fired off the edge of a desk. And we will see if the optimum angle, the angle that gives the furthest range or x distance, changes in these two scenarios. The projectile in this case is a ball bearing fired out of a spring-loaded device. You push the ball bearing into the device until you hear a click. There are actually three settings, three different clicks, but only ever fire it from the first one, as the second and third ones fire it too far for the experiment. Also, by using the same setting each time, we have the same initial velocity each time and a constant test condition. To release, you just pull up the little lever. By showing the projectile in slow motion, we can see the path that it traces out. And looked at side on, the path is the parabolic path of a projectile. The key parameters of this are the distance travelled x, which we'll measure, the height reached y, the time it spends in the air, the initial velocity v0, and the angle at which it is launched. The equation that links these quantities together is shown here. It's based on the simple equation of motion at a constant acceleration s equals ut plus a half at squared. In this case, the a term, the acceleration, is 0. We assume that the projectile moves in x at a constant velocity. In other words, if you were to look at its shadow, it would move across the table at a constant speed. In reality, air resistance will slow it down, but in this case, not as much as would make a difference to the calculations that we do. The y direction displacement is shown here, and in this case, there is an acceleration, g, the acceleration due to gravity. And you'll also notice in this equation that it's negative. In other words, compared to the positive direction of velocity, the initial launch velocity upwards, the acceleration will pull the ball bearing downwards. So it's a negative sense of the direction of acceleration. But we only focus on the x direction displacement, the range of the projectile. The three measurements in green are the ones we will actually record. We'll calculate V0 as a check of accuracy. The x displacement is easily measured. We do it with a ruler, and we use, as we'll see in a second, a little bit of carbon paper to mark where the ball bearing lands. Time is measured with an iPhone actually, or any smartphone, by recording the sound file, the click of the launch of the ball bearing and the noise it makes when it hits the hard table are very clearly marked on any sound recording. So if you look back at the sound wave, you'll see where those two events happen and work out the time very easily. And the angle we will set each time as our control variable in the experiment. And the V0, or the launch velocity, we just calculate from the equation I showed earlier. This is just a check. It's just to show in different trials at different angles that we're getting a constant V0, just to give us an indication of how accurate or repeatable this experiment is. So plot the values of time and displacement against the angle of launch for the two scenarios, and see what angle of launch gives the maximum distance, the maximum range of the projectile, and also see, is this angle, this optimum angle, the same for the first scenario launched along the table as it is in the second one off the side of the table.